Okay, so today we're going to talk about dependent events. And I already gave you the words, you don't have to fill in the blanks here. Two events are dependent events if the occurrence of one event affects the probability of the second event. So an example of this would be drawing cards without replacement. Say you're drawing a card from a deck and you don't put it back. If you don't put it back, then there's not the same number of cards in the deck, so the probability is going to be affected. Usually dependent probabilities involve things like drawing cards from decks or drawing beads out of a bowl, or beads are always a big thing, marbles out of a bag, things like that, where you can't replace an item, you don't replace one. In the game of Mahjong, picking a tile without putting it back would change the probability of getting another tile. Okay, our formula, if A and B are dependent events, we have probability of A then B equals the probability of A times, so we multiply, times the probability of B after A. What? It'll make more sense when we do a couple problems. So we're just taking the probability of A. It's still the same formula, really. We're taking the probability of A times the probability of B. But if we drew a tile and we didn't put it back, that probability changes. B would have been different before we did event A.
That thing after A, what is that?
It's the end of the parenthesis.
Wait, no, not that one. The other
times?
A. The other A.
This
wait.
one?
Is that like the?
That's the multiplication.
dot
Yep.
thing?
That's the multiplication dot. Okay, so here's our problem. This will help it make a little more sense. Suppose you choose a tile at random from the tiles shown in the previous example. So in your notes, you can see the slide with the Mahjong tiles there. Without replacing the first tile, you select a second tile. What is the probability that you choose a dotted tile and then a dragon tile? So we're just going to be multiplying the two probabilities. First of all, what's the probability that you're going to choose a dotted tile? Kira. Looking at that picture of the Mahjong tiles, how many of them are dotted? 4 out of how many are there? Good. So that first probability is 4 out of 15. Now, if we pick that dotted tile and we don't put it back, how many tiles are there on the board now?
14.
There's 14. Good. So now what's the probability that you're going to draw a dragon tile? Kyle? Since that rhymes with tile. Kyle?
3 out of 14.
Good. 3 out of 14. So there's still 3 dragon tiles left on the board, but there are only 14 tiles now because we used up one when we drew the first tile. Does that make sense? Okay. Multiplying, I'm going to cross simplify. 3 goes into 15 5 times. 2 goes into 4 twice, into 14 7 times. I get 2 out of 35. So the probability. Bless you.
Did you see my face? It was coming up.
She didn't hear that one. She was listening to the thing.
Okay. Emily, just so you know, that was Jackie who sneezed.
Oh, thanks. Thank you.
Okay, so our probability of both of these events happening is 2 out of 35. All right, let's take a look at the next one. What is the probability that you will randomly choose a flower and then, without replacing the first tile, a bird? Noah, what's the probability that you're going to randomly choose a flower?
1 out of 15.
Good, just 1 out of 15 because we only have one flower out of 15 tiles. Okay, now what's the probability? You did not replace that tile, so it's gone. What's the probability that you are going to get a bird? Rebecca? Good, 2 out of 14. I can simplify a little bit here first. And I get 1 out of 105. So the probability of those two events happening is even less. If we were to figure out the percent, 1 out of 105 gives us 0.009. So it's not even 1%. The chances of that happening are almost 1%, but not quite. Did you have a question about that?
No, but like, I feel like it should be more than 1%, like, it should be at least 1%, like.
Well, it's very close, 0.009, which would round up to 1. So it's close. Okay, any questions about this before we flip the slide? Okay, let's look at another example. Anybody want to read this?
I will read it.
Okay, read nice and loud, so Emily can
One
hear.
freshman. One freshman, 2 sophomores, 4 juniors, and 5 seniors received top scores in the school essay contest. To choose which 2 students will read their essay at the town fair, 2 names are chosen at random from a hat. What is the probability that a junior and then a senior are chosen?
Okay, thank you. Okay, so first, what's the probability that a junior would be chosen? Carly?
Okay, for juniors, so 4 over.
Over 12, good. Okay, now remember that the junior is gone from the hat. Okay, so what's the probability now that a senior would be chosen? Cameron? 5 over? No? Remember, we drew that name out of the hat, right? There were 12 names in the hat. How many names did we draw out already? No? The probability was 4 out of 12, but how many did we actually pick out that first time? 1. We just picked 1 because you picked that 1 junior. So how many are left in the bag? 11. There we go. So 5 out of 11. I'm going to simplify before I multiply. And you get 5 out of 33. Okay, let's try this one. It says bag contains 4 red chips, 3 green chips, 6 blue chips, and 5 black chips. Andrew selects a chip at random. He replaces the chip and then selects another one at random. What is the probability that he selects a red chip, then a black chip? Now are these events independent or dependent? Independent. I'm hearing some independence, 1 question mark. It's independent because he's replacing the chip. So what he picks the second time, it doesn't matter what he got the first time because he put it back. So this is a key word here. He replaces the chip. If it's replaced, it's independent. If they don't replace it, it's dependent. So what do we do to find the probability when it's independent like this? Right again?
We use like the same thing, like the same way, but you don't take one away.
Well, we're not taking away at all because it's not an or. But, well, okay, I see what you're saying. You're saying about taking away, you don't take one away from the bag, is that what you
Yeah.
mean? Yes. So you're still going to multiply, but that second is not going to change. You're still going to have the same number of chips in the bag. Rebecca?
Would you do 4/18 times 5/18?
Yes, you would. 4/18 because there's 4 red chips times 5/18. There's still 18 chips in the bag because he put it back. So we end up with, I'm going to definitely simplify first. 2, 9, I can simplify here. I get 5 over 81. Okay, then the problem changes a little bit. Now, Andrew selects a chip at random, does not replace it, then selects another chip at random. What is the probability that he selects a blue chip, roll this up, then a green chip? Is this problem independent or dependent? Stephanie? Dependent. Why?
Because it doesn't have the.
Right, it doesn't have the same number, he doesn't put the chip back this time. Okay, so what's the probability that he's gonna select a blue chip, Anthony? How many chips are there?
18.
18 chips, so 6 out of 18. Okay, then what's the probability that he's gonna select green chip? Claudia? 3 out of 17, good. Okay, I'm gonna simplify here also. If you do the fractions on your calculator, it'll do all the reducing for you. When I'm multiplying fractions, I always look, can I reduce up and down? Can I reduce diagonally? It just makes my answer already reduced, it's nice and neat. Okay, any questions? Okay, your assignment is going to be in class. We have about 20 minutes left. I have 2 worksheets for you to work on. One is very quick.
You said that last